Hello everyone, and we are on to page 41 today. We are doing more composition of trig functions. The big difference between what we did yesterday on page 40 and today, though, is that with composition of trig functions, we're switching it up and changing it and putting multiple trig functions together. So before we only did inverse sine of inverse cosine, or inverse sine of sine, or inverse cosine of cosine, right? We kept them together. Now we're changing it up. You can see in these notes, we got cosine and sine mixed together, or tangent and cosine mixed together. So we can't use the properties we did yesterday where we just canceled out and got the solution as the exact same. We're gonna have to really think about these and be very confident with our unit circle. If the value is not in the unit circle though, you're just gonna have to draw a picture. There is an example of that on here, but that one's actually, honestly, I think the easier of the ones. Knowing the unit circle is definitely the tricky part. You gotta have that memorized. If you don't, and if you haven't gotten that down yet, if I haven't said it enough, you gotta know the unit circle. It's gonna make this a lot easier on you. So let's look into this first one. You can see the directions just say that you're always gonna work from the inside out, kind of like we did on example 3 yesterday. So taking a look at this first one, example 1, it's asking us to do these compositions where we have multiple trig functions. So part A says, the inverse cosine of the sine of pi over 6. So what we're going to do is we're going to leave the outside exactly as it is. Inverse cosine. The only thing I'm going to care about solving is the inside first. What is the sine of pi over 6? So I'm going to look at my unit circle, or I'm going to pull it from my head. I'm going to think about pi over 6. And I know that's the y coordinate, so it's going to be 1/2. Cosine inverse of 1/2. So then all I have to ask myself is, when does cosine equal 1/2 using the restrictions we talked about? We know cosine is restricted from 0 to pi. So when does cosine give us 1/2 between 0 and pi? And that is definitely going to be at pi over 3, positive pi over 3. So that will be our solution. When I come over to B, again, leave the outside as is, arc, tangent. We're going to solve the inside though. What is the cosine of 0? So cosine is representing the x-coordinate, so I need the x-coordinate at 0 when we haven't even moved. So that's going over 1, so the cosine of 0 is 1. Again, thinking about our inverse tangent. Inverse tangent is always between negative pi over 2 to pi over 2, excluding those though. You can't equal negative pi over 2 or pi over 2. And so we have to ask ourselves, when does tangent give us 1? Hopefully you've kind of been practicing looking at that. We know that the only time tangent equals 1 is when the tangent's y divided by x, right? So when the y and the x are the same number, which happens at pi over 4. And in this case, we want it to be positive 1, so it's going to be positive pi over 4. Over in part C, the inverse sine of the tangent of negative pi over 4. So inverse sine keeps the same. When does what is the tangent of negative pi over 4? Well, at negative pi over 4, we got square root of 2 over 2, negative square root of 2 over 2. So that would divide and give us negative 1. Right, y divided by x, negative square root of 2 over 2, and positive square root of 2 over 2 simplified to 1, and we keep that negative sign. So when does sine equal negative 1? Well, again, we know sine is between negative pi over 2 and positive pi over 2, including those this time. So when would we get negative 1 from sine? So it's going to be at one of the poles. It is the y coordinate, so it's got to go down 1. So it's going to be at negative pi over 2. It's going to be at the bottom of the unit circle. And of course, this last one over here says arc sine, and they asked us to find the cosine of 5 pi over 6. I know that my pi over 6 cosines are always square root of 3 over 2, but in this case, it's going to be negative. So negative square root of 3 over 2. And we're going to go ahead and then figure out the arc sine. Again, we have the same rule we just used before, negative pi over 2 to pi over 2. So since it's negative square root of 3 over 2, I know it's going to come from quadrant 4. And we know that sine is always going to do that at the pi over 3 markings. So in this case, I'm going to have negative pi over 3 as my solution. So all of those you can see are situations that we did where the regular trig was on the inside and the inverse was on the outside. Kind of helpful to keep that in mind because it's less important in this section than it was in the last section, but it definitely helps a little bit in this section in figuring out where these pieces go. All right, example 2, you can see these ones have the inverses on the inside in this case. So same idea, we're going to solve the inside first and then do the outside. So in this case, we've got cosine, and it says the inverse sine of 1/2. So we got to use the rule right at the beginning here. So in this case, the rule was inverse sine. So we know sine has to be between negative pi over 2 to positive pi over 2. So we're just trying to figure out where 1/2 would happen between negative pi over 2 and pi over 2. So since sine is the y-coordinate, I believe that's going to be at positive pi over 6. All right, so we got that. Now we just got to solve that last part, which since we did the hard part in the beginning, this part's pretty easy. What is the cosine at pi over 6? Well, the cosine at pi over 6 is going to be the x-coordinate, so square root of 3 over 2. That box did not go in the right spot. All right, and into example B here. This time we have cosine of the inverse tangent of square root of 3. So again, thinking about inverse tangent, we know that it's between negative pi over 2 and pi over 2. So we're trying to find situations where tangent would be between that. Well, if you think about that chart from yesterday, I know that might be a throwback to have to go back there, but knowing what those tangents are, it does help a little bit. We know that tangent is always square root of 3 in situations of pi over 3. Pi over 3, 2 pi over 3, 4 pi over 3, or 5 pi over 3. Those are the spots that you would expect tangent to be square root of 3. So I know that this is going to come out to cosine. And like I said, it was pi over 3. And since we know that it's going to be between negative pi over 2 and pi over 2, and it's positive, it's just going to be at positive pi over 3. Notice all of this is just confidence with that unit circle. That's all I'm using is my unit circle confidence. All right, cosine of pi over 3. If I look at cosine, we know it's the x value at pi over 3. The x value is going to be 1/2. All right, coming over to part C, sine of the arc cosine of 0. So arc cosine, we know that arc cosine is always between 0 to pi. So we got to pick an answer between 0 and pi that would satisfy that. So sine of cosine 0, the x-coordinate would be 0 at pi over 2, correct? Going straight up. That's where we would get 0. So then it says find the sine. Well, at pi over 2, what would be the sine? We're going to look at the y-coordinate this time, and the y-coordinate would be positive 1. So sine is going to be, sine of the arc cosine of 0 is positive 1. All right, and on to our last example. This one is that one that we said if the value is not in the unit circle, that little part that I underlined right here, that right there, since 8 over 17 is not a value on the unit circle, so we can't use our unit circle to solve this, meaning we're going to have to draw a picture to find this exact solution. And that's what we're going to start by doing. The first thing I'm going to do over here is just draw a coordinate plane. I didn't want that to be sideways. Try that again. There. I'm glad this will fix those straight lines because that was terrible. So we know that cosine has to be in which quadrant. So the first part I'm focused on is that the cosine inverse can only be between 0 and pi, meaning it's in quadrant 1 or quadrant 2. And since it's positive, so we know that this has to be in quadrant 1. So immediately I know that I can put a point in quadrant 1. Again, the reason being, cosine is only positive in quadrant 1 and quadrant 4, but we're not allowed to use quadrant 4. We're restricting it to 1 and 2 only because that's between 0 and pi. So what I know then is that this is going to represent the triangle that we're talking about here. So we're focused on this triangle. We also know that cosine is if you think back to cosine was, we addressed it as cosine of theta is always equal to x over r. Those are the letters we changed into here. You may also know it, though, as SOHCAHTOA, adjacent over hypotenuse. Doesn't matter to me which one you're using as long as you are aware of what it means. So what this means is that this 8 represents the x-coordinate and 17 represents the r. So 8 has to go here, 17 has to go here. So if I wanted to find the tangent now, we know that tangent needs to know tangent of theta is the y value divided by the x value. Or again, you may know it as SOHCAHTOA, so opposite over adjacent. Well, in this case, I already know the x value is 8. That part I have. That was part of kind of the given. What I'm missing is what the y value is. So I'm going to need to use just some Pythagorean theorem to find that, right? We know the Pythagorean theorem, a squared plus b squared equals c squared. If I do that, I can find this missing side. So I'm going to make 8 squared plus the missing side. We got to set the hypotenuse as c, so make sure you always put the r or the hypotenuse as c. And we're going to solve that. So 8 squared gives us 64. 17 squared is 289. I'll subtract 64 from both sides here. I get b squared equals 225. And square root both sides, and I get b equals 15. So I now know that this represents 15. So we can address this question now. The question was, what is the tangent of theta? So the tangent of theta equals the y value over the x value, so 15 over 8. And that would be the solution we're looking for. So all it was is just taking the pieces we know, plugging them in, and then solving for that missing one on the outside. Hopefully that helps you a little bit. Come to me if you got any questions. Best of luck on this. Goodbye, everybody.